My next presentation now is on single station fee using mainly the NGA West 2 data, and I am acting as a proponent expert. I am going to talk briefly, give a background on single station fee, terminology used and the approach. I saw that Norm covered that earlier on, so this will be brief. Then I'm going to show the results of the single station fee analysis using NGA West 2 residuals from Abrahamson et al., Campbell and Buzornia and Chu and Youngs, as well as using residuals from the Taiwan data of the Lin et al. Paper. I'll show some observed trends with magnitude, distance, VS30, and some comparisons, and I will also, hopefully, if I have enough time, cover some path effects and regional variations and try to explain some of these things. So here, this is the plot that you just saw before. So we have the total residual, which is the misfit from observed ground motion with respect to the GMPE for an earthquake E at a station S. And this is usually divided into two components: between event residual, which is the average of the misfit for one earthquake, and within event residual for each recording for an earthquake, which is the misfit between the recording at this particular station and the event-specific median. So again, terminology, delta BE is the between event residual that used to be called, or sometimes is still called, inter-event residual or event term. Delta WES is the within event residual or intra-event residual at station S for earthquake E. Now, if we look at the standard deviations of the between event residuals, we have tau, between event standard deviation, and phi is the within event standard deviation, and when we combine them, we get sigma, total standard deviation. So when we talk about partially removing the ergodic assumption, what we basically mean is if we have enough recordings of the ground motion at an individual station, we can estimate the systematic side effects and remove them from the within event residual, and this way we can get to single station phi. So this delta S to S term that we estimate represents the systematic deviation of the observed amplification at this site from the median amplification predicted by the model. So this here summarizes the terminology used. So I have from the different models that I am analyzing, their within event residuals. I estimate the site-to-site term. So this one does not include the event term in it. I estimate the site-to-site term. I take that out, and I end up with single station within event residuals, and then single station phi. And this is all what I'm talking about today. I'm not talking about tau. All right, so we start with the Abrahamson et al. Residuals. If I choose a minimum of 3 recordings per station, I end up with 13,000 recordings from the Abrahamson et al. Model, 297 earthquakes, and over 1,000 stations. Most of these recordings come from California, and you can see here magnitude distance distribution. Some of the data is from Taiwan, and fewer data from Japan, Italy, and China. So this is the frequency of the recordings versus VS30, and this is just the recordings that remain after I consider only a minimum of 3 recordings per station. And you can see most of the data comes from VS30 between 250 and 700 meters per second. This plot here shows the number of recordings used per spectral period, and you can see here that the number of recordings drop after about a period of 1, and this is due to the minimum usable frequency of the data. So let's see the difference between the phi and the phi-SS for the Abrahamson et al. Residuals. In red here you have the phi, which is the ergodic fee, and in blue you have this single station fee for all the data together, all the region groups together. And you can see here the difference that you get after taking out the side-to-side term. Now, if we want to look at this plot region by region, you see here the triangles are the California data. So you have here the fee for California as a triangle. In blue, it's the FESS for California. Then you have the square, it's the Japan data. This is their fee, and this is their FESS. Now these stars are the Taiwan data. So fee for Taiwan is significantly lower than the rest of the data, and same thing for FESS. So if we can also add Italy, which is the circles, and there is not that much data, so you can see that it has a big error. So if we look at FESS only here, to make it more clear, you see the FESS of all the data set. Then you have California, Japan, Italy, and Taiwan here. So I looked at the impact of my minimum number of recordings on the results. So maybe 3 is too little. I looked at using 5 and 10. So it's a trade-off between how reliable is the side term that I take out versus how much data I end up with. So for n-min equal 3, 5, or 10, this is the California FESS, and actually doesn't change because there is so much data for California that it just doesn't matter. This is for Taiwan, n-min 3 and 5. If I take n-min 10, I don't have any Taiwanese data. And it also is okay either way. This is for Italy, and it's not okay either way, so because there isn't that much data. So from now on, I will show results for n-min equal 3 in order to keep as much data as possible. So this is here a comparison of the FESS of the whole data, all the regions together, using n-min 3, 5, and 10. And you see 10 is slightly higher, but that's only because we don't have Taiwanese data anymore, which was bringing the FESS down because it was significantly lower than the rest of the regions. Okay, so let's look at some magnitude dependence. You have here first plot PGA, period of 1 second. And this is FESS versus magnitude, split up by regions. In blue, the circles are California, and you see it's about constant up to magnitude 5, then it drops, then it goes slightly up again, and it goes constant. For Taiwan, and this is the stars in red, most of the data basically groups around 3 magnitude ranges. China is these triangles, and there isn't a lot of data. And then we have Japan, it only groups in this magnitude range. For a period of 1 second, again, this is California here in blue, and the FESS slightly increases and then decreases again from magnitude 5 onwards. Now, let's look at the magnitude and distance dependence. So we group the data in different magnitude bins and distance bins. And this is PGA, California only. In blue is the magnitude 3 to 5, red is 5 to 6, and green is 6 to 8. And one obvious thing to notice here is how the FESS jumps up for the small magnitude at short distance. This sort of behavior, I don't see it with magnitude 5 to 6 and 6 to 8. This is the same sort of plot for Taiwan, but we only have magnitude 5 to 6 and 6 to 8. I don't know if we can say much about it. This is the Japan, and it's only magnitude 6 to 8. And this is here Italy, and we only have 5 to 6 and 6 to 8, and with a lot of error. These are the same plots at a period of 1 second. For California here, notice that we don't have this ramp up of the FESS with a small magnitude short distance. Pretty much looks more or less constant. This is Taiwan here for a period of 1 second, Japan, and then Italy. VS30 dependence, so I grouped the residuals in different VS30 bins, and we have California in blue, and it actually shows a little bit of an increase in VSS as VS30 increases. This is for PGA, and then for 1 second, it increases a little bit, then decreases again for California. Okay, for the Chu and Young's for NJ West 2 residuals, I repeated the same analysis. Using a minimum of 3 recordings per station, I get over 9,000 recordings, mainly from California, and few hundred recordings from Japan. Just to show their phi and VSS, this is their ergodic phi, and after taking out the side term, this is the VSS that we get for their residuals. Now I'm showing then the phi and VSS for Northern California and Southern California, and it's kind of interesting to see that for phi you see some difference in Northern versus Southern California, but when you take out the side term, they kind of collapse. And here adding the Japan data, this is the phi for Japan, the squares, and this is in blue, the VSS for Japan. And I'll show more trends later on when I compare everything together. For Campbell and Bozornia, using a minimum of 3 recordings per station, I have over 5,000 recordings, and I have the residuals up to 80 kilometers, and they're mainly from California. These are their phi and VSS, and this is all the data, and the triangles are California only. All right, so then I analyzed the Lin et al. Data, and this is mainly to try to understand why is the Taiwan VSS smaller than the California VSS when I look at the Abrahamson et al. Residuals. So I basically have the Lin et al. Residuals for Taiwan, and they have basically over 10 recordings per station in their data set, and I added to those whatever additional residuals were in the Abrahamson et al. Data set. So I have a total of about 5,300 recordings from 65 earthquakes at 362 stations. And this is the phi and the VSS that I get. VSS is about 0.4, and again it's also smaller than California. If you recall, it was about 0.5. All right, so now I'll compare all these results together and see where they are different. So looking at the 3 NGA-West 2 models that I analyzed, this is VSS for California, and it agrees very well among all the models. This is VSS Japan for Chu and Young's 13 and Abrahamson et al. And again, they kind of agree. And these are the Taiwan the Taiwan VSS using the Lin et al. Data mainly with the additional residuals from the Abrahamson et al. Versus using only the Abrahamson et al. Residuals. So I'm sorry, this is Abrahamson et al. And this is Lin et al. So you see that the Lin et al. Is slightly higher. For the Abrahamson et al. Taiwan data, they basically had Chi-Chi main shock and 5 aftershocks, so the Lin et al. Has a lot more data. Let's look at the magnitude dependence of all the models together, and we have, I'm only showing California for the NGA-West 2 models and also Taiwan from the Lin et al. So for the California NGA-West 2 models, they kind of agree, all the models in terms of the magnitude dependence. Taiwan is over here, it shows some trend, but it's smaller VSS. This is PGA, this is a period of 1 second. Magnitude distance dependence, this is interesting here. You see magnitude 3 to 5, 5 to 6, 6 to 8 at PGA. And see here, all the NGA-West 2 models have the same VSS and the same trend. Basically high VSS for small magnitude short period. The Taiwan, the Linetal data shows also the same trend. However, the VSS starts dropping lower compared to the California data at larger distances. For magnitude 5 and 6, NGA West 2 models show similar VSS trends, same thing as Taiwan, and magnitude 6 to 8, kind of similar trend. This is period of 1 second. Now Taiwan agrees very well with the California data. VS30 dependence, again, all the 3 NGA West 2 models showed the same trend of increased VSS with VS30 at PGA. This wasn't observed for the Taiwanese data. You can see it's more or less constant. This is PGA and this is 1 second here. So I think Adrian in the previous workshop gave a presentation about the VSS models that were developed for the Pegasus refinement project. And this is here one of the plots from their report. This shows phi, which is the ergodic within event standard deviation, for the different regions that they used. They had data from California, Switzerland, Taiwan, Turkey, Japan, but they had significantly less data than what we have now for NGA West 2. And you can see here the trend basically that there are regional dependence in phi. However, when they took out the side term, things looked more stable. So one of the conclusions at the time is that there isn't regional dependence, which isn't what I see now with the Taiwanese data. So at that time they had 3 VSS models. One is constant, one is distance dependent only, and one is magnitude and distance dependent. So I'm going to compare the California VSS to the constant and the MR dependent VSS from the Pegasus refinement project. This here shows in red, this is the VSS versus period for California, and this is from the Abrahamson et al. Data, but it's the same for all the other models. This line here is the mean VSS for the constant PRP model, and then plus and minus 1 sigma. And right now it appears that our California data is on the higher side compared to the mean of this model. If we look at, compare again California binned by magnitude and distance and compare that to the MR dependent Pegasus refinement project models, you see here in blue solid line is the magnitude 4.5, in red is the magnitude 5.5, and in green is the magnitude 7. Right now I see stronger distance dependence here for California data than what was suggested in the Pegasus project. They also saw more of that distance dependence for the middle magnitude range, magnitude 5 to 6. I don't really see that anymore, and it's more or less similar for the magnitude 6 and 7. At 1 second, they also had this distance dependence, and now the California data, we can argue that maybe there isn't such distance dependence here at short distance. I don't know. So it's similar, but there are some differences. So observations is basically, right now the main issues is VSS from this analysis does not necessarily appear to be region independent. So we clearly saw that, especially Taiwan, where we had a lot of data, well, enough data, had lower VSS. One thing I looked in the Lin et al. Paper, and actually also another study, Chen and Tsai 2002, reported a low VSS too for Taiwan. So there is clearly something going on there that they have a smaller VSS. So I looked into the effects of path on this VSS, and I'll get into that in a minute. The other thing that we observe is this increase in VSS at small magnitude and short distance. And we want to try to understand why this is happening. Is it hypocentral location errors? Is it radiation pattern? And I also looked into that a little bit. This is all work in progress, but I'll show some things. So path effects, I One thing with the path effects is we can look at the closeness index as a proxy to see how paths are similar. And this is, based on the Lin et al. Paper. So basically, if you have a station here that recorded 2 earthquakes, you can compute the closeness index for the path from these 2 earthquakes to this station, and this is equal to the difference in the hypocentral location divided by the sum of the distances to the station divided by 2. So what this says, basically, this CI can be a number from 0 to 2. If it's 0, it means that the earthquakes are co-located, they have the same path. If it's 2, it means that they are in opposite epicentral directions from the site. So what I did is I tried to see what would be the expected closeness index for randomly located earthquakes around the station, and I compared what is the average closeness index that comes from the data to that random one to see how much, how random are the path or how similar they are. So for the expected closeness index for randomly located earthquakes, I just generated a series of randomly located earthquakes in a circular area around a station, computed CI for each pair of earthquakes, calculated the mean CI, and repeated this for different number of earthquakes and different distances around the station to see how stable this number is. And basically, this comes out to be about 1.38 CI. And here we go again, missing symbols. But that's CI. So then it's about 1.38. Let's look at the Northern California data. So if I compute the CI for all the Northern California data in the Abrahamson et al. Residuals, and I plot them here, I have on the vertical axis delta square, where delta, all what it is that it's the normalized difference in the residuals, normalized by the phi-SS. One thing we can see is the distribution of the closeness index, and it appears that a lot more is closer to 2. One thing we can do here, and this is based on the Lin et al. Paper, is we can compute the standard deviation. I can basically bin these delta squared in different closeness index bins and compute the standard deviation sigma. And this is what you see here with these data points. The solid line is the model that was proposed in the Lin et al. For Taiwan data. What this means is that basically if your closeness index is 0, it means your paths are perfectly correlated, then you are here, and this would be, will give you the single path sigma. That is normalized in this case because we're normalizing. If your closeness index is 2, meaning your paths are not correlated at all, then this will give you the single station sigma. This is 1 because it's normalized. And anywhere in between, it means you have some path effects that are being observed. So this green line here, green data point is the closeness index for randomly located earthquakes, the 1.38, and if I average all these closeness indexes here, I get 1.16. So basically what this tells me is there isn't much path effects for the Northern California data. Same thing for the Southern California. The exact same analysis, and I get a mean closeness index of 1.2.
Linda, I think that's, it's not that there are no path effects for Northern California data, but you don't have unusually repeated paths, right?
Yeah, like they're not clustered.
They're not clustered.
Yeah. For the Taiwan data, and this is why we looked into these path effects, this is, this also was done in the Lin et al. Paper, so I repeated it, and it's the same exact thing. These are the closeness index and the delta squared, the normalized residual squared, and these are the sigma. And on average, the closeness index comes as 1.02. So it's not single path, at least. So then I thought that where we observed this lower VSS for Taiwan is for magnitude 3 to 5 at longer distance. So I thought maybe if I look at this subset of the data, I'll see them clustered at a smaller closeness index, but no. So I don't know what to say about why Taiwan is having low VSS. It's one of two things. Either it's just low for that region, or that this approach of looking the path effects for some reason isn't working. But I have to look more into that. So epistemic uncertainty of VSS. Well, like Norm said earlier on, when we do this partially non-ergodic approach, we need to estimate the site-to-site term, and the TI team will need to do that, but we'll also need to consider the epistemic uncertainty around this site-to-site term. Another epistemic uncertainty that needs to be considered is around the single station phi. And one way we can do that is we can look at the single station phi at every station and see the distribution and their standard deviation. So this is, for example, for the California data, so we need to use a larger number of recordings per station. This is the VSSS, basically VSS at every station, their distribution. And if we want to assume that this is log normally distributed, we can get a mean and median VSS and this standard deviation, which can inform our epistemic uncertainty. So, do I have more time? Okay. Another thing we're trying to understand is can the radiation pattern explain the high VSS for the California and Taiwan in this case for magnitude 3 to 5 and short distances. So for California data, we had these S-wave radiation coefficients in the flat file that approximate the finite fold radiation pattern of the hypocentral for the FN and FP components. But this was missing for a lot of the data, particularly for the small magnitude data. So Doug here did some simulations and took these small magnitude events and calculated an effective radiation coefficients for this data set using Green's function for a central coast 1D model. So basically, this radiation coefficient is the ratio of the maximum amplitude at the station relative to the maximum amplitude over a ring at the distance of that station. So this is period independent, and this one too is period independent. So what I tried to do is to plot the within event residuals versus this radiation pattern and grouped by these magnitude distance ranges. So this is here for M3 to 5. The blue under this one is distance 0 to 15 kilometers, and the red is 15 to 30 kilometers. And we can see some trend of the residuals with increasing the radiation coefficient. This is for magnitude 5 to 6 and 6 to 8, and not much trend is observed. So then I went and I binned these residuals and computed VSS in the different radiation coefficient bins. So you have here the dark blue is M3 to 5, distance up to 15 kilometers. And we see this kind of ramp of the VSS as the radiation coefficient increases up to 1. This other, another kind of blue here is the M3 to 5, distance 15 to 30 kilometers, does not show such a strong trend. And then M6 to 8 and 5 to 6 also don't show trend. Now this, I put this plot here just to remind us what we're kind of looking for. We're looking to explain this increase here. So I honestly don't know yet what this means. I think that maybe it kind of explains some things, but I don't know if this is the whole story. So this is work in progress. If anybody has any ideas, you're welcome to speak.
Is this your last plot?
No, but it's similar ones. 1 second. So here you see more the radiation pattern impact at longer periods. But the interesting thing is when I bin them up, kind of I don't see pattern of VSS here, which I also don't see in the VSS versus distance. Summary, that's it.
Okay, so Let's start with those last couple of plots, because I'm not sure I understand what, go back one more. Actually, let's go forward one. So the bottom plot is what we're trying to explain.
Mm-hmm.
And this large increase, right?
Yes.
And so my concern before had been numbers as high as 0.9 compared to, let's say, 0.5.
Yeah.
If the standard deviation is going up that much, you must be adding variability that itself is 0.8 or something like that, right?
Yeah.
It's a huge term. So now when you go to the go back one, I guess it is, we're trying to look at, I don't understand what you just did on the top frame of the next plot. So here, you're trying to look at, yes, there's a slope, right? And how much that radiation pattern would be increasing the variability of PSS. But what did you do on the next one?
What I did is I binned these residuals in different radiation coefficient bins, and I plotted them. And my hope was to see like magnitude, R0 to 15 here, but then R15 to 30 back.
So go back one again. So I'm still a little trying to figure out what we're trying to show here. We want to know impact of radiation pattern, but you're applying the standard deviation about the average line? So would it be about the blue line? Because if there was a really steep slope, so radiation pattern was having a large effect, we could still have the same standard deviation and it's having a big effect. Really, I thought we want to look at the impact of the slope here.
So this standard deviation is basically just the square root of these residuals divided by n. So I don't take out the mean.
Oh, so it's all about zero.
Yeah, it's about 0.
Okay, all right, so that helps. So part of this is if there was a steep slope, and we talked the other day that blue line would have to have a slope of maybe 3 times what's shown there to really
explain.
to get it from radiation pattern.
Yeah.
But if you go to your next one now, so I know what you're doing, on the right-hand side, you're showing more variability when the radiation pattern should be high.
Yes.
Right? Meaning sometimes it's working and sometimes it's off, or maybe we actually have the wrong radiation pattern in there because of, I'm not sure how accurate that is.
Yeah, there'll be uncertainty in the radiation pattern for the small events. I guess the other factor though is the hypocentral coordinates in particular source depth.
Yeah.
But if we go back, she's taking the square of the residuals with respect to 0. So if the whole thing is moved off, you'll get a sigma from the bias. So that would also increase the standard deviation. If that's what you're doing, then
Yeah, that's what I mean.
that would improve. So she's getting the shift of the mean off of 0 for the high radiation coefficient.
Can we go to 1 second? I was going to say, because it seemed like there was a very large slope, like, I guess go forward to, from,
It's definitely steeper.
yes. I was going to say, also, you'll have the
But
negative slope on.
but the mean residual where all the data is centered at 0, so you don't have the effect of the offset. And then as you move down,
You have that there.
so it's not. So the other one was centered where at high radiation coefficient it was off 0, and this one it's not.
Yeah. Sorry to confuse you, but I'm also confused.
Well, this is a topic we need to try to understand. The radiation pattern was a very appealing idea,
Explanation.
if that would get it. So this explains some of it.
Some
right?
of it. I
So
see.
we're back to how much does your standard deviation go down
if I take
when
that
you,
out.
when you took that out.
Yeah,
That's,
I
I guess.
haven't yet done that kind of stuff. Yeah.
So one of the comments or questions for all of our resource experts here, this picture on the bottom is something we have to try to understand why that standard deviation goes up so much at short distances for small magnitudes. If it had been the other potential explanation was an error in the hypocenter location, which would have a bigger effect on the short distances, right? And that would, so if it was off by 5 kilometers, we might be able to start to make a large effect. But it seemed like it was having to be off by more than what the reported errors are going to be in those things, right? Because they're going to be on the order of kilometers, do you think, on this? Or?
For source depth, several kilometers.
So, what about Adrian? Can see this in Japan?
Yeah, I have to say that, so Yusuf asked about the Japan data from Adrian, and actually Adrian is doing a lot of work using the Japanese data, and this is something that we will have in the next couple of months or so, right? I'll let Adrian speak for that.
So this time being here, one of the issues with PGA is at short distances, it's dominated by very high frequencies, and at large distances, it's dominated by lower frequencies. Lower frequencies routinely show better radiation pattern than high frequencies. If you go to high frequencies, you're hard pressed to see radiation.
But that would push us the other direction.
Other direction.
Because we're thinking radiation pattern is going to then emphasize a larger variability than if it's all washed out. So we tried those ideas early on, and they're pushing us the wrong way. Yes.
This is okay. This is new to me, so I may have missed something here. Is this effect? Did I see correctly? This is not seen at 1 second.
Yes, that's right. So here is the plot. This is 1 second. And not, I mean.
So any radiation
not
pattern
much.
like that type of explanation would have to explain the difference between the high frequency and low
Yes.
frequencies. Or likewise, any hypocentral distance
Yes,
explanation.
yeah, exactly.
I think you're right, Steve, that this tells us radiation pattern is likely not to do it for us. This feature was seen though with all of the GMPs, right?
All the GMPs and for the Linetal data, Taiwan show the same thing.
Are these the killer pulses?
Yeah, magnitude 3s. Go ahead.
Yeah, a number of questions. So you see,
Gabe,
yeah, Gabriel
give your
Torres.
name.
Gabriel Torres.
Thank you.
I think my accent is recognized already, but anyway. Yeah, Linda, so you see this with the GMPs that use JB distance as well?
No, I don't have it actually.
You don't have it, because it could be the rupture distance just doesn't work well for these short distances. And it may be a matter of just looking at the residuals very carefully.
So one thing that might do it on depth is we have pretty strong depth scaling. And Z-Tor or hypocenter depth in the other one. So that emphasizes the hypocentral error. And I think that's getting back to what you're saying, just we're moving things almost a factor of 2 for every 10 kilometers, the hypocenter moves up and down. So, especially for small earthquakes, some of them are really strong. So that might be driving. I think you need to almost run a simulation of errors in the hypocentral depth to see if we can produce that, assuming the models are right even in the way that they predicted the depth scaling. Because I don't think the distance changed from 10 to 12 kilometers or whatever the slope is, this distance will be is going to be a large enough effect. But the depth scaling may be what's blowing that up at smaller magnitudes.
Yeah.
And the other?
Do they have? But when Adrian and founded for Pegasus, were they using JB distance or using rupture?
Just one quick question. A couple of very quick questions. First, another thing we need to consider is that the duration of these motions is going to be very short and may contribute to the scatter. And second, does this have any implications when you try to use small event data to empirically characterize your site terms?
It makes it more difficult because there's more scatter,
Okay.
but we don't think we're biased.
So it's less informative,
It's less informative.
Okay.
Right.
and that's taken into account in the procedure.
Correct.
Okay.
That's part of the range of the sigma SSs or phi SSs that Linda was showing. So to answer, could you just give Adrian the microphone? Just describe what you did on the Pegasus work.
We use closest distance in the Pegasus work, and we see the same trends only for small. We see distance dependence only from small magnitudes, except that we only went down to magnitude 4, so we didn't see it spike up as much. Norm, you mentioned we could use simulations, but you can also use Bayesian methods in which you introduce uncertainty in depth and see how much of that takes away from the resulting PSS.
Right. I think there's a bunch. One is just the size of the effect. Can we get there easily, incorporating a couple of kilometers, 1, 2, or 3 kilometers uncertainty in the depth? So you could do it formally with Bayesian approach, or she can just brute force run it and see, are we in the right ballpark here? Can you get the number up to 0.9, assuming the underlying variability was really a half? Because this is all influencing us in terms of what do we do for larger magnitudes. One is to ignore that, but we need to have a good explanation for why that effect should not be addressed.
Does it matter to the hazard? Because this is happening at magnitudes 3 to 5.
Yeah, no, it doesn't matter if we say that only applies to small magnitudes and doesn't apply to big magnitudes, but we have a lot of data from these small magnitudes and not as much from the other ones, so close in, so I think we really need to have a good reason to say this model is not applicable to the high magnitudes. Gabe, you need the microphone.
And it also matters, as I said earlier, when you do empirical site-specific estimation of the site term, that is going to matter as well.
Right, that influences your ability, how much epistemic uncertainty you need, and how many earthquakes you need to constrain it.
So that has hazard implications.
Correct.
Okay.
Correct.
Even though those events themselves don't contribute to the hazard. That
Right,
information.
especially anytime you're using the smaller earthquakes in particular. Yusef?
Yusef Uzornia. Adrian, for Japanese, you have magnitude 4 and above or 3?
The Japanese data that I have worked on so far is only magnitude 4 and above.
Okay.
And we are now processing data down to magnitude 3, but that's not, we haven't done the analysis
Okay.
yet.
And then, Linda, 2 things. I gave you residuals for our model up to 80, but I have it up to 300 also, so I can give it. Then other things that I noticed for NGFS2, the difference between phi and phi SS is about 0.17, something in that order, 0.15, something.
Mm-hmm.
But if I recall correctly, for NGFS1 was in order of 0.1 or so. Do you recall?
So Norm, you did the NJ West one, or I did it? I don't remember.
I was trying to think of what I was going to write down. Say that again, Yusef.
For the difference between phi SS and phi in NGFS1, if I recall correctly, was close to 0.1. Now it's 0.17.
We didn't do it as, we did it in terms of the total when we were reporting it. So sigma versus sigma SS, it was about 15% lower.
Okay, I was curious.
15% of the value, so it's about 0.1 unit down.
So I was curious why we get more reduction. Is it because we have more data?
No, phi is going to come down more because we're going to add the tau term into it, right?
But the difference in NGFS1 between phi and phi SS, was it order of 0.1?
We didn't,
Oh, you didn't?
I didn't tabulate it that way, that's what I'm trying to say, so I don't know that number.
Oh, I see, okay.
We have it reported as an impact on the total segment because that's what we were scaling off
I
of.
see, okay.
So if the total comes down by 0.1 natural log units, then the FESS must come down by more than that because we're going to be bringing the tau term along, right? Christine.
So, yeah, you mix your girls. So yesterday, actually, I had a discussion with John Ake about that and this whole issue of the larger sigmas at the small magnitude. I really think, well, Norm, we haven't talked about it yet, but at least for NGEs, we'd like to do simulations, like Gabe suggested, just basically on the randomizing maybe the magnitude and sampling that, and also distance, because the uncertainty on those small events, I think, is probably what is driving that. And we'd like to compare that to what we observe.
Right, but I think here it's not distance, I think it's depth.
Yeah,
Because
well,
we have
that's
such a strong depth term.
Exactly,
right?
but you could
The
do
effect,
as well for
right,
that.
sure.
Exactly. And I think that would be a really nice exercise to do, just SMSim, run a bunch and run statistics and see if it replicates what we see here instead of assuming a deterministic value.
But she can just also take the GMPEs
Oh,
and
yeah, and
propagate
change
it
it.
through there.
Yeah.
And then see would they be producing this same size of an effect. If that makes it work, then we can associate it with the hypocentral depth error, and we have a reason for why that is limited to that size earthquake.
Because if you're using a point source, then you have to assume some depth dependence model for stress drop.
Other comments? Adrian, did you have something else? Okay. We're actually right on time, Linda, so thank you. If there's nothing else for Linda, I think what we're set out is moving forward, we still have to figure out the explanation for this. But you're getting fairly robust numbers, at least between the GMPE values, right?
Yeah.
Can you put that back up, just
The GMPs,
the three approaches or models?
Sorry.
And you just haven't run Bohr yet, is that
Yeah, I
right?
haven't done it because I didn't have much time, but I didn't have the residuals, but I'll get it.
And Taiwan
this
is the Lin et al.
Yeah, the
data.
Lin et al. Plus your additional residual.
Okay.
Which don't make a lot of difference because they have most of the data.
So the 3 to 5 is really similar,
Yeah.
other than Taiwan.
Mhm.
And the 5 to 6 is still pretty good, so. So 0.4 to 0.5 in the mid-range, and then even 0.3 to 0.5 for the bigger earthquakes. All right, any last questions? Or Paul, can you pass the microphone to Paul?
Norm, I'm wondering if the smart array data in Taiwan, which give information on spatial variation, might be of some use here. Could sort of help resolve whether there's different spatial coherency issues in Taiwan compared with, say, California, that might affect this.
Yeah, that's over really short
Right.
separations.
Right. But it might give you some idea of how quickly things get incoherent, because that should affect maybe one aspect of this issue.
One aspect. So far, we've been using data from Taiwan at those short distances to move them to California because we haven't had as much tight spacing. I think Jack is going to talk a little bit about that on a larger scale, right? So when Jack is talking about directivity, he's also going to be looking at this spatial correlation issue. And so let's think about that as well. Have you we'll wait till then, but if you've only looked at California, or have you looked at different regions, okay? And that might be what we need to do. Adrian?
I'm trying to understand what is the difference between Taiwan and California. Is Q more uniform in Taiwan than it is in California? We have seen the maps for Q for California. Are there similar studies for Taiwan?
I don't know that answer. We have a couple folks from, person Lynn is actually here today, which is nice, but I don't know if you have any comments or know about Q models. Are there Q maps for Taiwan that are?
We do have some Q study in Taiwan too, so maybe I can find out the reference for you to look at.
Part of the issue, I think, is sampling the paths as well. And kind of what Linda was trying to get at was this closeness index, but that may not be capturing everything. If most of the paths are along the western side of the island, okay, you may have something that's much more uniform because there's more stations there and so forth, as opposed to paths that cross through the mountains to the other side. So it might just be a more uniform sampling north-south that is dominating the data sets. We didn't look at sort of azimuthal variations that we're not seeing in California, where we're having more variability in the paths. So this closeness index is our crude way of trying to avoid binning things up into cells, but it has a whole lot of other limitations that or features it's not capturing. Yes.
Linda, this is Jennifer Donahue. Question for you. In one of the first slides that you showed, it looked like Taiwan was binned up about the same with Italy. So this is like, pretty far at the beginning.
Yeah.
So I guess my question is, I don't know, is it easy to find that one?
About Italy.
Right, so
Oh, you want to see that slide, okay. So it was kind of similar sort of VSS for Italy, and the Italian data and norms model was also a lot of aftershocks. But I did not do, I kind of did the closeness index plots for it, but I didn't really show it because there isn't that much data, so I just concentrated on Taiwan. But yes, this is Italy here.
Okay, so it looks like they're basically following each other. So I was just wondering if maybe we're having the same problem with that data, or it's just not showing up. So I think you've answered my question.
Yeah.
Okay.
So Jennifer, we had speculated that because in this data set, a lot of them were aftershocks, that they were just repeated paths coming through. So that was our first thought at it. Yeah. Anything else for Linda?
I have a question for John Anderson. So John Anderson from University of Nevada, Reno, online, asking, have you looked at any correlation between VSS and kappa?
Somehow it all goes back to kappa, unfortunately. No, I haven't. Does he have any ideas about
that? A bigger, so Yusuf will probably tell us, what we need to get is kappa for all of these stations, and that's a big effort. So if John would ask that question in about 2 years, we probably will be able to address it. But until you have enough kappas in the data set, we can't start to get at that just yet.
Yeah, and I think we probably see the kappa effect when we see the VS30 dependence, that increase, maybe due to variability in kappa, I don't know, could be. Because we take out the mean kappa.
You've taken the site out, so kappa should be gone from here, right?
Yeah, but the variability around the mean, I don't know. It's just a speculation.
So what would a lower kappa lead to more variability? That's what you're speculating, right?
The other way around, right? Yeah, you're right.
Lower kappa, so lower kappa is going to let more high frequencies through, and maybe there's more variability that way.
I don't know.
Does anyone else want to speculate or discuss the role of cap? I mean, there is clearly something going on here
Yeah.
with an increase there, right?
Yeah. Adrian didn't see the S30 pattern.
Ken?
Just an observation that for the path effects, you're using this closest index, which is interesting, but it's possible that path effects, another factor would be distance. So even if you have the same closest index, if you're 100 kilometers away versus 10 kilometers away, you know, you do have, in fact, even though the path may be similar, but if there's errors along that path, they're going to accumulate or something. So I don't know if that's easy to test, but distance could be a factor. Sorry, this is Ken Campbell.
Yeah. There's clearly room to improve that parameterization of of the similarity of the paths. All right, let's move on. So we're trying to stay on schedule.